Welcome back, everybody. Mr. Johnson with you again. This is Lecture 28 on hybridization. We are on page 395 of our ebook, and we're actually not going to use our book much for this lecture, as the visuals in here aren't great, and to me the explanation is a bit incomplete. So we're going to use a video I found on YouTube, along with a bit of me explaining, to hopefully have hybridization make sense. This is one of those lectures that's pretty abstract. There's some pretty tricky concepts in here. So I hope that this makes sense, but if it doesn't make total sense to you, but at least at the end of the day, you're able to identify the hybridization around an atom and figure out how many sigma and pi bonds there are and be able to describe vaguely what a sigma and a pi bond is, you're going to be in great shape. That's my goal for you today. All right, we're going to start our discussion with a video from Crash Chemistry Academy, the best and most succinct video I could find on YouTube. Here we go.
Hello and welcome to a video about hybrid orbitals, often called valence bond theory, developed in the 1930s by the great chemist Linus Pauling as a model of bonding to understand the three-dimensional placement of atoms in a molecule, and that is critical to our understanding of the properties that molecules have. In this video, we will look at methane, ethene, ethyne, ammonia, and water as our models for hybridization. There is only a small group of atoms in the second period that the model really works for, but among those are carbon, nitrogen, and oxygen, which make up the vast majority of molecules that exist on Earth. So the model applies to a limited number of elements, but it applies by far to the majority of molecules. Let's take a look at the word hybrid. It is a blending of two varieties. If you get a horse and donkey together, you get a mule, a blending or hybrid of a horse and a donkey. Let's get to hybrid orbitals, using carbon as our model. As a single atom, not bonded to anything, carbon has 2 electrons in 1s, 2 electrons in 2s, and 2 electrons in 2p. This electron configuration is the energy arrangement of carbon's electrons. However, carbon rarely exists in nature as an individual atom, except momentarily while undergoing chemical reactions. Carbon exists with its valence electrons bonded to other atoms. When carbon bonds to 4 other atoms, carbon's 4 bonds are experimentally seen to be equivalent. And so when the carbon atoms finds itself in a bonding situation, its bonding electrons themselves exist at equivalent energies, which requires that they hybridize to an energy that is intermediate between the 2s energy and the 2p energy. Or you can think of it as a blending or hybridization of the two energies, the s and p energies. And since the energies of these electrons have now changed, the shape of the orbitals they occupy are different as well, which we will see momentarily, and those are called hybrid orbitals. They are named 2sp3 hybrid orbitals. The naming often trips up students, so before we go any further, let's take a look at where the 2sp3 name comes from. The 2 comes from the second principal energy level that the valence orbitals are in. The s comes from the 2s orbital contributing to the hybridization, and the p comes from the 2p orbitals contributing to the hybridization, and the 3 comes from the number of 2p orbitals used in the hybridization. Once hybridized, the 2s and 2p orbitals no longer exist, and so we have 4 2sp3 hybrid orbitals. 4 2sp3 hybrid orbitals derived from combining the energies of 1 2s orbital and 3 2p orbitals, which gives a total of 4 2sp3 orbitals. Before we look at the shape of hybrid orbitals, it would be helpful to briefly review the atomic orbitals. The 1s orbital is a sphere, the 2s orbital is a larger sphere surrounding 1s, and here we will get rid of 1s since we are only concerned with the valence electrons. Each 2s orbital is a 2-lobed shape converging at the nucleus. So there are the 3 2p orbitals. However, when hybridization occurs, the s and p orbitals cease to exist, and the 2sp3 orbitals have an entirely different shape. We can see that orbital hybridization explains the VSEPR placement of carbon's 4 valence electrons, since all 4 2sp3 orbitals are equivalent. Each 2sp3 orbital repels the others with equal force, resulting in identical bond angles. The carbon atom only hybridizes when it is in a bonding situation. Here, 4 hydrogen atoms bond to carbon by overlapping their orbitals with carbon's hybrid orbitals. So what would be the reason for this? If we go back and see that both carbon and hydrogen have unpaired electrons, the overlap allows the electrons to pair and thus go to a lower potential energy. The illustration here contains the valence electrons of both carbon and hydrogen, and since everyone likes to visualize atoms as spheres, we can do the same. Here is our carbon atom, and here are the hydrogens with the overlapping spheres, indicating the overlapping orbitals that constitute the bond. The bonds are more readily discernible in a ball and stick model, which also makes the bond angle more visible. Since all 4 sp3 orbitals are equivalent, each bonding orbital repels the others with equal force, resulting in identical bond angles. The bonds in hybridization also have their own nomenclature. The overlapping orbitals are called sigma bonds, which represents the single bond occupied by a single pair of electrons. What about double bonds? How does the hybridization model explain double bonds? We will use ethane C2H4 to see what happens in a double bond. The single bonds we know are sigma bonds, and the double bond also has a sigma bond, but the second bond of a double bond is a pi bond. Let's see how hybridization and orbital overlap can explain a double bond. The 2 carbon atoms in ethane are equivalent, so let's look at one of the carbon atoms first. A pi bond comes from the overlap of unhybridized p orbitals, and so the atom hybridizes only 3 orbitals, leaving a p orbital unhybridized for the pi bond. The hybrid orbital is called 2sp2, the superscript 2 denoting that only 2 2p orbitals have contributed to the hybridization. The 2sp2 hybrid orbitals exist in a plane perpendicular to the unhybridized 2p orbital. Let's remove the 2p orbital for now to more easily see that. The 2p hybrid orbitals are spread out at a 120-degree angle, which means that they exist in a plane, and the plane is perpendicular to the unhybridized 2p orbital. So this is what both carbon atoms do when bonding occurs in ethane. Each carbon atom is sp2 hybridized. The sigma bond occurs with 2sp2 orbital overlap. What about the pi bond, the second bond of the double bond? Previously we said that it comes from the unhybridized p orbitals, which we see here from both carbon atoms. The top and bottom lobes of the 2p orbitals overlap above and below the axis of the sigma bond, forming a single pi bond, the space in which the now paired electrons move around. The ball and stick model shows this double bond with 2 dashes. To summarize, sigma bonds occur along the axis between nuclei. The pi bond occurs above and below the sigma axis, where the p orbital lobes have overlapped. The ethane molecule also bonds to 4 hydrogen atoms by overlapping with both carbon's other 2sp2 hybrid orbitals, creating 4 more sigma bonds. In the ball and stick model, we can readily see that each carbon has a trigonal planar geometry, and thus the whole molecule exists in a plane with the single pi bond above and below that plane. Now let's look at how hybridization can be a model for the triple bond using ethyne C2H2. The carbon-hydrogen bonds are sigma bonds, and the triple bond is 1 sigma bond and 2 pi bonds. Let's see how hybridization can accommodate this. Since pi bonds come from p orbitals, and we need 2 pi bonds, then 2 2p orbitals have to remain unhybridized, and so the remaining single 2s orbital and a single 2p orbital will hybridize to 2 2sp hybrid orbitals. And there is also the violet 2px and the blue 2py orbitals. Here each green lobe is a single orbital, and so they each have an electron, While both violet lobes constitute the single 2px orbital with a single electron, and both blue lobes constitute the single 2py orbital with a single electron. The other carbon in C2H2 also has that same triple bond, and so it has the same hybridization. Let's see what happens during bonding. sp orbitals from both carbons overlap, forming a sigma bond. The upper lobes of the blue 2p orbitals overlap, as do the lower two lobes, creating the first of the two pi bonds. Can you guess where the second of the two pi bonds comes from? Yes, that's right. It is the overlapping of the violet 2p lobes. Let's get rid of the sigma bond for a moment to take a look at something interesting. Each pi bond lies on a separate plane, and the two planes are perpendicular to each other, and so the two pi bonds are perpendicular to each other. Finally, two hydrogens will overlap with the remaining sp hybrid orbitals, creating the C2H2 molecule. The overlap of the space-filling model reflects the overlapping orbitals, which is also represented by the ball and stick model. In the remainder of the video, we will look at hybridization of nitrogen and oxygen using NH3, ammonia, as our model for nitrogen hybridization, and H2O, water, for our oxygen model. In NH3, nitrogen has 3 sigma bonds and a lone pair. So how does hybridization account for this? The hybridization is 2sp3, and nitrogen has 5 valence electrons, so one of the 4 2sp3 hybrid orbitals has a pair of electrons. The 3 sigma bonds come from the sp3 orbitals with a single electron, so they can pair up, and so the remaining electron pair is a lone pair, an unbonded pair of electrons. As with sp3 hybridization in carbon, nitrogen's hybrid orbitals spread out in a tetrahedral shape. And lastly, water. Here, oxygen has 2 sigma bonds and 2 lone pairs. In water, oxygen is also 2sp3 hybridized, but with 6 valence electrons. 2 of the sp3 orbitals have paired electrons. You can probably guess that the sp3 orbitals with a single electron will overlap with hydrogen, and the remaining 2 pairs are unbonded. They are lone pairs. Again, oxygen's hybrid orbitals spread out in a tetrahedral shape. That's it for hybridization, the product of a mad scientist.
All right, I am back. So we just learned that atomic orbitals, the spherically shaped s orbitals and the hourglass or dumbbell shaped p orbitals, when atoms bond, hybridize, mix, and create these similarly shaped hybrid orbitals called sp or sp2 or sp3 hybrid orbitals. We heard that when an s orbital hybridizes with 3 p orbitals, we get sp3 hybrid orbitals, and that would mean there's no unhybridized p orbitals. If an s orbital hybridizes with 2 of the 3 p orbitals, leaving an unhybridized p orbital, we get sp2 hybridization. And that unhybridized p orbital tends to form a pi bond. If just one s orbital hybridizes with just one p orbital, leaving 2 unhybridized p orbitals behind, we get sp hybridization, and those unhybridized p orbitals tend to form 2 pi bonds. So we'll talk more about that and see the pattern. We heard that a sigma bond, which is a single bond, is due to the overlap of hybrid orbitals, along the internuclear axis. And that's what's written here in purple. Sigma bond, also a single bond, is the overlap of hybrid orbitals along the internuclear axis. A pi bond, though, which will always be the second bond in a double bond, or the second and third bond in a triple bond, come from the overlap of unhybridized p orbitals above and below the internuclear axis. Or if there's an additional pi bond, if there's 2, then one would be above and below, and the other would be in front and behind the internuclear axis. So that's a quick review of sigma and pi bonds, and then we'll try to cut to the chase here with another chart. Ideally, everything you just heard makes sense, and you'd be able to now figure out the hybridization and how many sigma and pi bonds there are in a molecule or on any given atom. But That's typically not the case. So this chart is meant to help distill for you those key concepts and those key skills. There's ultimately three things you need to be able to do about hybridization. One is to be able to identify the hybridization around a particular atom in a molecule. It's just one atom at a time whose hybridization can be determined. In addition to that, you want to be able to identify how many sigma and or pi bonds there are in a molecule or around a particular atom, and that's the easiest skill to typically do. And the third thing is to be able to explain or define what a sigma bond and or a pi bond is, which is what the last slide was about, and we'll come back to again in a bit. All right, so that first skill, how to identify hybridization. Well, there's three kinds of hybridization you need to know about: Sp3, Sp2, or Sp. So, are there three electron geometries we've learned about in here: tetrahedral, trigonal planar, and linear. And those, as you know, come from 4 electron groups, 3 electron groups, and 2 electron groups, respectively. Well, when there's 4 electron groups around a central atom, and the electron geometry is tetrahedral, that is always Sp3 hybridization. When there's 3 electron groups around a central atom, which is trigonal planar electron geometry, that's always Sp2 hybridization. And when there's just 2 electron groups around a central atom, and it's linear electron geometry, that's always Sp hybridization. 4 electron groups, Sp3, 3 electron groups, Sp2, 2 electron groups, Sp. So down to this 4 electron group region of the table, remember, if there's 4 electron groups, that doesn't mean they're all bonding groups. They could all be bonding groups, and then it's a tetrahedral molecular geometry, or 3 of them could be bonding groups, and 1 of them could be a lone pair. Or 2 of them could be bonding groups, and 2 of them could be lone pairs. But in all 3 cases, it's Sp3 hybridization. Remember, Sp3 means that an s orbital and all 3 of the p orbitals hybridized. There's 4 hybrid orbitals. Well, if there's 4 bonding groups, which means there's 4 single or sigma bonds, we should know those all come from hybrid orbitals. There's 4 hybrid orbitals, 1 for each of the bonds. That's why it's Sp3. But if there's 3 bonding groups, 3 single bonds, 3 sigma bonds, and a lone pair, it's also Sp3 hybridized. That's because the lone pair electrons are always in a hybrid orbital. So there's a hybrid orbital for this bond, a hybrid orbital for this bond, a hybrid orbital for this bond, and as well for the lone pair, which is why it's Sp3 hybridized, 4 total hybrid orbitals. Same thing for 2 bonding groups and 2 lone pairs. Each of those bonds is a sigma bond, which always comes from a hybrid orbital, and each of the lone pairs is in a hybrid orbital also, giving us again 4 hybrid orbitals, or Sp3 hybridization. Well, if all 4 electron groups are bonding groups, we know there's 4 bonds. A single bond is a sigma bond, so in that case there'd be 4 sigma bonds. But in NH3, with just 3 single bonds, there'd be 3 sigma bonds, and with water and just 2 single bonds, there'd be 2 sigma bonds. So now we're looking at Sp2. We should know that Sp2 means that 1 s orbital and 2 of the 3 p orbitals have hybridized. There's 3 hybrid orbitals. 1 of the p orbitals is unhybridized, and that's typically due to a pi bond. So if there's 3 electron groups and they're all bonding groups, that would be in one of the incomplete octet molecules like BH3 or ALH3. We'd have 3 single bonds. They're each sigma bonds. There's no lone pairs. There's only 3 hybrid orbitals. It's Sp2. If, though, there's 2 bonding groups and 1 lone pair, that's usually going to come from a double bond, a single bond, and a lone pair. That's also Sp2 hybridization because the sigma bond in the single bond is a hybrid orbital. The first bond of this double bond is a single bond. That is a hybrid orbital. And the lone pair is a hybrid orbital as well. So those are 3 hybrid orbitals giving us Sp2. And then the second bond in the double bond, the pi bond, comes from unhybridized p orbitals, which is why it's Sp2, not Sp3. And we'd see 2 sigma bonds here, a sigma in the single, a sigma in the double, and then 1 pi bond is the extra bond in the double bond. And we already know if it's linear electron geometry, or there's two electron groups, it's sp hybridized, which means that one s orbital and one p orbital have hybridized, meaning two of the three p orbitals have not. And that's typically going to come from two double bonds or a triple bond and a single bond. Two pi bonds, meaning. Each of the sigma bonds in the double bond is a hybrid orbital, so that's where we get sp. And then the second bond, the pi bond, comes from the two unhybridized p orbitals. So here's why we've got two sigma bonds and two pi bonds. So whether all that makes sense and the patterns make sense, at a minimum, remember, two electron groups, whether bonding pairs or lone pairs, sp hybridization. Three electron groups, whether bonding groups or lone pairs, sp2. And four electron groups, whether they're all bonding pairs or some of them are lone pairs, sp3. Each single bond is a sigma bond, a double bond has a sigma bond and a pi bond, and a triple bond has one sigma bond and two pi bonds. All right, so we're going to finish this lecture with some practice problems. These are all XAP multiple choice questions. All right, first question. The hybridization of the carbon atoms. It's a symmetrical molecule, so both carbon atoms are essentially the same. In the molecule represented above can be described as sp, sp2, sp3, and these other ones we've never heard of, so just imagine that D and E aren't right because we've never heard of them. All right, well, each carbon atom has four electron groups surrounding it. Four single bonds, four sigma bonds. Four electron groups surrounding an atom, which, by the way, is tetrahedral electron geometry, four electron groups. Sp3 hybridized. All right, next question. What is the hybridization of the carbon atoms in a molecule of ethyne? Of course, this was one of the molecules in a lecture represented above, but it's off here to the right. And it's symmetrical, so both carbon atoms are essentially the same. Well, we could count electron groups. There's one electron group and another one. Remember, a triple bond counts as an electron group. Two electron groups around a central atom / linear electron geometry. Two electron groups, sp. And by the way, the number of electron groups adds up to the number of s's and p's combined. There's one s and one p, two electron groups. sp3, on the other hand, one s plus three p's, 1 plus 3 is 4, would come from four electron groups in the prior problem. Again, this is sp hybridized because there's two electron groups around each carbon / it has linear electron geometry. Furthermore, we should know that the second and third bond in the triple bond are pi bonds. Each pi bond comes from unhybridized p orbitals. There's two unhybridized p orbitals, which takes us down from sp3 to just sp. All right, third practice question, maybe just two to go. When reaction 3 occurs, does the hybridization of the carbon atoms change? When reaction 3 occurs, does the hybridization of the carbon atoms change? So reactions 1 and 2 are decoys. We're just looking at reaction 3, and we're looking at the carbon atoms in the reactant compared to the product. And it must be, again, these are symmetrical molecules, and that the hybridization in both carbon atoms on the reactant side are the same, and the hybridization of the carbon atoms on the product side must be the same as well. To do this, you've either got to visualize the Lewis structure or draw it. So let's draw it out so we can more easily determine the hybridization on the carbons on the reactant side and product side. All right, there are Lewis structures for C2H2 and for C2H2Cl2. Didn't walk you through those steps, assuming you can do that, but do be aware that if there's ever more than one carbon in a molecule, they always connect. The carbons always form the skeleton or the backbone, and then other things attach. That's why I hooked the two carbons together in both of these. Well, in C2H2, each of the carbon atoms, again it's symmetrical, has just two bonding groups. Excuse me, just two electron groups, and they're both bonding groups. Two electron groups / linear geometry, sp. S plus p equals 2. So, sp. Meanwhile, on the product side, C2H2Cl2 has this structure. Looks like each of the carbon atoms has 3 electron groups coming off of it, 2 single bonds and a double bond. 3 electron groups / trigonal planar electron geometry is sp2. The s added to the 2 p's gives us those 3 electron groups. So we're changing from sp to sp2. By the way, in this molecule above in blue, there's one sigma, one more sigma, 1 pi, one more pi, and another sigma bond. So by the way, there's 3 sigma bonds and 2 pi bonds in this molecule, whereas down here there's 1, 2, 3, 4, 5 sigma bonds and 1 pi bond. Just a little side note. Consider giving this one a shot on your own. You'll have to draw Lewis structures for all these, and then seeing if you got the same answer I did. Which of the following molecules contains exactly 3 sigma bonds and 2 pi bonds? Again, you'll either need to picture these or draw their Lewis structures to figure that out. Try it on your own, come on back. See how you do. All right, here's ethyne once again, which has 1, 2, 3 sigma bonds and 2 pi bonds. Remember, each single bond is a sigma, and the first bond of a multiple bond is sigma. Any additional bonds are pi. So 3 sigma, 2 pi. I'm thinking A is going to be our right answer. Let's just check B, C, D, and E. In B, there's 2 sigma bonds and 2 pi bonds. Remember, each bond of the double bond is sigma, every additional bond is pi. So it's definitely not B. C looks like 1, 2 sigma bonds and 2 pi bonds also. So again, we already know it's A, but we're ruling out these other ones. D, 3 sigma, 3 pi. And then in nitrogen, 1 sigma, 2 pi. So definitely A. Same thing, consider giving this one a try. I got to draw Lewis structures for these. Can't ever practice Lewis structures enough. Come on back, see how you do. Meanwhile, say this is a multiple choice question on a unit test or an AP test. You scan these, you look at E, you look at CH4. Ideally, you've drawn CH4 enough to know it's got all single bonds, tetrahedral geometry, 4 electron groups, no pi bond. So it's definitely E. And if we look at the rest of these, all these other molecules have at least 1 pi bond in them because they all have at least a double or a triple bond. C6H6, by the way, is called benzene. It's this molecule over here. We saw it in our group problems. It's a 6-carbon ring with alternating double and single bonds. We may talk about it more if we get to organic chemistry, but it's worth recognizing the structure of benzene. Again, C6H6 is benzene, 6 carbons in a ring, alternating single and double bonds, and then each of the carbons has a hydrogen coming off of it. By the way, this molecule exhibits resonance. When we have alternating single and double bonds like this, the double bonds aren't localized between any 2 carbons, but are shared evenly, because those double bonds, instead of being where they are, could be where the single bonds are, and they're in neither place. They're everywhere at once, which is crazy. Speaking of crazy, let's just get a little reckless here at the end of this lecture and identify the hybridization on these carbon atoms. If you want to pause and figure out what these carbon atoms hybridizations are and come back, you can. Otherwise, here we go. This carbon atom has 2 electron groups coming off of it, and it's got linear geometry, 2 electron groups, sp. Each of these carbons, it's symmetrical, have 3 electron groups coming off of them, trigonal planar geometry, sp2. This carbon atom, ooh, funny little guy here, has 1, 2 electron groups coming off of it. Remember, lone pairs count as electron groups. 2 electron groups, sp hybridization. And that lone pair, by the way, will be in a hybrid orbital. So will the sigma bond, but the pi bonds won't. All of these carbon atoms have 1, 2, 3 electron groups coming off of them. Trigonal planar electron geometry and molecular geometry, sp2 hybridized. And then good old methane, 4 electron groups, tetrahedral geometry, sp3 hybridized. 4 sigma bonds. And then I'll leave you one last time with what sigma and pi bonds are. Sigma bonds, remember, also called single bonds, are the overlap of hybridized orbitals along the internuclear axis. Pi bonds, on the other hand, come from the overlap of unhybridized p orbitals. It's the second bond in a double bond, or the second and third bond in a triple bond, above and below, or in front of and behind the internuclear axis. That's it, folks. Lecture 28. It's come to a close. Hybridization. Have a great day. Be kind to each other. Make the world a better place.